So let's talk now about orthogonal matrices. All right, that's a definition first. What's an orthogonal matrix? It's a matrix such that its transpose times itself is equal to itself times its transpose is equal to the identity. In other words, what does that mean? What is the definition of the matrix such that if you multiply it on the right or on the left by the original matrix, you get the identity? It just means that its inverse is equal to its transposed. Okay? All right, so you very simply have that an orthogonal matrix is a matrix such that its inverse is its transposed. Next comes just a piece of vocabulary. We're going to call the orthogonal group, and using the notation ON of R or O of N, the set of all orthogonal matrices. Okay? Next, let's give some very fundamental example. All right. So, it's going to, that's really the fundamental example. All orthogonal matrices can actually be expressed as this example. All right. So we have two orthonormal bases, right? So E1, sorry, the first one. Okay, our B with E1 up to En, and we've got a second one, B prime, from E1 up to En prime. So when I can write, that's going to be better. Okay, and of course, you know the nicest thing to do when you've got two different bases is to write a change of basis matrix. The one, and you know that you remember that if you have X that is expressed in your B with your original B matrix, okay, so XB, let's call it this way, it's equal to some matrix P times X prime, the components of X in the basis P prime. Why do I write it this way? Because this is usually the matrix that is the simplest to express. Usually you have the coordinates of the new basis with respect to the former basis. Okay, maybe the original basis B is the standard basis, the 1 0 0 0 1 0, etc., and B prime is anything else that you can imagine, as long as it's also orthonormal, right? And so usually you get the expression of E prime, of the E prime's vectors with respect to the standard basis, if that was your P matrix that you started with, okay? And so again, sorry, so again we have, if the columns of this matrix are the components of the E prime vectors in the E vector spaces, well, you know that these components are given by this relation. That's what we saw just previously. The components are given by the scalar product of the two vectors, all right? And so you can express explicitly the components of this change of basis matrix, right? The same way, if I want to do the contrary would be to say, well, actually I've got X B prime is going to be equal to something. What is the something? It's actually P minus 1. Okay, I just apply P minus 1 on both sides of the previous equation. So X prime B is P minus 1 times XB. All right, so I know that if I want to do the contrary, to go from coordinates in the former basis to the coordinates in the new basis, this is one way to do it. Okay, but another way to do it would be just to rethink that in terms of change of basis. What do I have actually in what would be the matrix that I get here? The matrix that expresses the vectors E1, E2 up to En in my basis E1 prime up to E prime N. Okay, and so very similarly, any item of this change of basis matrix contains any columns, contains the coordinates of the vector ej in the new basis e prime 1 up to e prime n, and so you get them exactly very similarly by saying that they're going to be these components are obtained by taking the scalar product of ej with the e prime k, the corresponding on the corresponding row, right? So that the ijth component of this matrix is gotten by the scalar product of ej e prime I. Okay, and but don't forget that this matrix, sorry, that's a scalar product. This matrix is also p minus 1. Okay, and so very naturally we get that the component of p minus 1 was actually the transpose of the previous one. Okay, and that works only when you have orthonormal basis, because only when you have orthonormal basis you can write this kind of decomposition, that the expression of a vector in that basis is going to be given by the sum of the inner products times the components of the basis, right? Okay, so that's a very fundamental example. Pause and redo it again by yourself, maybe starting from your blank document, so that you are sure to understand this one. Okay, so following this example, this fundamental example, you have this very naturally this proposition that tells you that actually you're going to get an orthogonal matrix. When you have an orthogonal matrix, either it's the columns make an orthonormal family or the rows make an orthonormal family, right? Why? Because very simply, if you've got that, you can re-express this matrix as a change of basis matrix from one orthonormal basis to another one. Okay, it's just a very direct observation that comes from the previous example, right? Either it's really a change of basis matrix, and so you can get we can show that its inverse is going to be its transpose if the bases are both orthonormal, or if it's if you don't know that, you can interpret the matrix as a change of basis. All right, very very naturally. All right, and the next theorem tells you that you've got an orthogonal matrix M, then it is invertible. Of course, that's the definition. Okay, definition just tells you it's orthonormal if we've got that, and that means that really means that mt is m minus 1. Okay, that's just the definition of orthogonal and definition of inverse matrix. And then we get that the determinant of m is plus or minus 1. Also, that comes very naturally from the properties of the determinant. So let's see the determinant of a product of matrices. Okay, so MMT, we know that it's going to be the same thing as the determinant of I, because the two matrices are the same. The determinant of I, of course, is 1, and the determinant of a product of matrices is going to be the determinant of the product of the determinants. But you also know that the determinant of the transpose is the same thing as the determinant of the matrix. So the determinant of m squared is equal to 1. So the determinant of m is equal to plus or minus 1. Okay, that seems very natural. Next, what do we get? We get another definition. So we had previously talked about the orthogonal group, and now we're going to get the special orthogonal group. right? And that would make a perfect band name, I think. And it has notation SO of n or O plus n of R. It's going to be all the orthogonal matrices that have determinant 1, right? We saw orthogonal matrices have determinant plus or minus 1. The ones with plus 1 are going to be the special ones, right? Okay, we've got this nice series of inclusions here. Okay, so the orthogonal group is a subset of the general linear group. Okay, I hadn't used that name yet, but I think I used the notation. It's the set of all invertible linear maps, linear matrices of size n on R. All right, so general linear group is the set of all isomorphism on or n. Right, so the orthogonal matrices are of course a subset of those because we saw that they were all invertible, and that's it. Okay. Um, and the special, of course, the special linear group, the special orthogonal group is going to be a subset of the general linear group because they are going to be invertible. Right, what comes next is if we've got two matrices that belong to the orthogonal group, or respectively to the special orthogonal group, then their product also belongs to the orthogonal group. Well, it's just going to, we just need to work on the, stuff. So, all right, so A and B are such that they belong to the orthogonal group, so it means that AT is A minus 1, BT is B minus 1. So what about A times B? Transposed. Let's multiply this by A times B. You know that the transpose of a product is the product of the transpose, but written in the other order, so that's going to be B transposed A transposed times A times B, and of course this is identity because we get AT is A minus 1, so that's equal to BT times B, and which is of course equal to the identity. Okay, so we proved that first part. Next one, if A is an orthogonal matrix, respectively a special one, then its inverse belongs to the set of orthogonal matrices. And well, I maybe leave that proof to you. What is A minus 1? Okay, if A is orthogonal, we know that A minus 1 is its transpose. So work on that. It's really a matter of writing that, not even one line. Okay, just note one thing, that if we've got an orthogonal matrix, we have that its determinant is plus or minus 1, but the reverse implication is false. If the determinant of A is equal to plus or minus 1, it does not imply that A is an orthogonal matrix. Okay, as a counterexample, you can think about 1, 1, 1, 0, right? I let you think about why, well, that has obviously determinant of 1, but why this is not an orthogonal matrix. Okay, so pause here and find out why this is not orthogonal.